talk about static malware detection. So this is work that I have been doing with my PhD students. So the number of new malware exceeds 413 million by the end of 2015 and is still increasing. There is more than 1 million new malware released every day. The number of malware that produced incidents in 2010 is more than 1.5 billion. For example, the war My Doom slowed down global internet access by 10%. And in 2008, there is a crash of a Spanair flight, and the authorities that were investigating the cause of this flight, they have discovered that the central computer system that was used to monitor the technical problems in the aircraft was infected by malware. That malware detection is very important. But you can tell me, yeah, but there are a lot of antiviruses that we can use. Yes, but these antiviruses, they have serious limitations. So the existing antiviruses, they are based on mainly two techniques. The first one is what we call signature matching, where every malware has a signature. So a signature is like a sequence of bytes that represents the malware. And so every antivirus has a database of known signatures of known malwares. And then given a program to determine whether the program is a malware or not, the antivirus will check whether it has one of the known signatures in its database. So if it has one, then it is declared as a malware. If not, it is declared as benign. So, but this technique has serious limitations because, and you can easily get around it. So how? So if you take a malware, then you can easily change its code, okay, in order to create a new code that has exactly the same malicious behavior than the initial malware, but with a different signature. And so its signature is not in the database of the antiviruses, and so they won't detect it. Okay, and malware writers, they know all this, and so this is why they update their malwares frequently in order to evade from malware from antiviruses. And this is why for every malware now, every malware has millions of variants. Okay, the other technique is code emulation that consists in executing the binary code in a virtual environment. Okay, but this technique, so if while executing the code, it reaches a malicious behavior, the code is declared as a malware. If not, it is declared as a benign. The inconvenience of this technique, the limitation, is that it can check the program's behavior only in a limited time interval, which means if the malicious behavior appears after this time interval, then it won't be detected. So then what we need, how can we have a robust technique? So what we need to have a robust technique for malware detection is to have a technique that checks the behavior, not the syntax of the program, and without executing it. And model checking is a good candidate for that. Why is that? Because model checking allows to check the behavior of systems without executing them. So this is therefore our goal. Our goal is to perform model checking for malware detection. So how are we going to do this? So a malware is an executable. This means it's a binary code. Thus, our goal is to check whether a binary code satisfies some malicious behavior. So for that, we need to find an adequate model, an adequate mathematical model that represents binary code, and an adequate specification formalism that represents malicious behaviors. So what is a good model for that? So there already exists some work that try to use model checking for malware detection. But these works, they would use finite automata to model the programs. But finite automata, they cannot handle the stack of programs. But the stack is very important for malware detection. Why is that? Because to achieve their goal, malware have to call functions of the operating system. And antiviruses will determine malware by checking the calls it will make, the program will make to the operating system. And so virus writers, they know all this. And so what they will try to hide the calls they make to the operating system. So how is that? So these are two equivalent programs. This program uses a normal call, and this one uses a hidden call. How is this? So these are the addresses, okay? So this is the return address of this call. So while reaching this point, what would the program do? This call, it will first push the return address L1 into the stack, and then it will jump to the entry point of the function f. So this means if I replace this call with a push to L1 and then jump to f, then I have an equivalent. I have a piece of code which is equivalent to this one, but where there is no call. Okay? And so to be able to precisely detect and analyze malware, we need to be able to analyze and handle such piece of codes where we have that handle the stack. We have push, we have pops, etc. This is why it's very important to analyze the program stack. And our solution to this problem is to use push-down systems to model programs. So roughly speaking, what is a push-down system? No need to read this. It's just a finite automaton equipped with a stack. And the stack is simply would be the stack of the program. It will model the stack of the program. So this is it. We are done with this part. So binary code, I will use push-down system to model them. Now, what about an adequate specification formalism to represent malicious behaviors? So for that, let me give you an example of a malicious behavior. So let's consider the malware Avron. Okay, so a malware, what does it want to do? It wants, one of its purposes is it wants to infect the maximum number of computers, of files, etc. And so to do this, let's see how the malware Avron does this. It will call the API get model handle A with 0 as parameter. By doing this, this function will return the entry address of its own executable. And once the malware has the entry address of its own executable, it will use it to copy itself to other locations. Okay? And so that it can infect other locations. Okay, so let's see how this is done in the malware Avron. So in assembly code, parameter passing is done through the stack. This means that calling the API, this API with 0 as parameter means calling this function with 0 on the top of the stack. So this function goes and gets its parameters from the stack. So this is how this is done in Avron. It will put 0, move EAX 0. So we will put 0 into register EAX. Then we will push EAX. So by doing this, we will have 0 on the top of the stack. Then I will call get module handle A. Okay? Now, how to describe this specification? One idea is to use branching time temporal logic. So this is just some logic. Don't worry if you know it. We just need the operator exists next, which means so this operator means that if I am in a state, then there exists a path from this state such that in the next state, P holds. Sorry. So I can then represent this behavior as follows. I have a move EAX 0, and in the next position, I have a push EAX, and in the next position, I have a call to get model handle A. Yeah, but here we use register EAX, but I could have used register EBX or any other register. This is why we need to take the disjunction over all the registers, okay? EAX, EBX, ECX, etc. And this would lead to a huge formula. Okay, so we obtain a huge formula. So the solution to overcome this problem of the fact that it's a huge formula we will use, we will introduce the quantifiers, existential and for all quantifiers. And then we can represent all this huge formula in a succinct way like this. There exists a register R such that I have a move R0, and in the next position I have a push to R, and then I have a call to this function. So this is how we obtain a compact representation of this malicious behavior. But still, this is not sufficient, because by doing this, we don't represent the stack. But the stack is very important here. Why is that? Because imagine I take this piece of code and I add to it push EBX followed by a pop EBX. Then this piece of code still satisfies this behavior, since get model handle A is called with 0 on the top of the stack, but this piece of code does not satisfy this formula. You will tell me, yeah, but I can add here, and in the next position I have a push, and then I have a pop. But this is not sufficient, because I could have added here 1,000,000 of pushes followed by 1,000,000 of pops. So what is the solution? Our solution is to use predicates over the stack. How is that? So this is a predicate that tells me I have 0 on the top of the stack, and then I have anything, and then doesn't matter. I can have anything. Okay? And then I can represent this, this specification using this formula that says I have a path where I have in the future a call to this function such that I have 0 on the top of the stack. Okay? And so you can see that this represents exactly this specification. Okay? And that this piece of program satisfies this specification. And even if I have, if I add 1,000,000 of pushes followed by 1,000,000 of pops, sorry, then I still satisfy this formula. Okay, so then that's it. To represent malicious behavior, we will use this kind of logic extended with all these, with variables, with quantifiers, and with predicates over the stack. And we can also use other logics which are more, sorry. We can use other logics. I mean, depends on the situation, depends on the malicious behavior. Okay, so don't worry about this. I mean, one of these logics can be used. So to summarize, to be able to apply malware detection for to be able to apply malware detection using model checking, we will represent binary code using pushdown system and malicious behavior using this kind of logics. And then to check whether the binary code satisfies the malicious behavior or not, we will check whether the pushdown system satisfies this kind of formulas written in this kind of logics. And so we proposed model checking algorithm to perform this step. And then we implemented all our techniques in a tool. So this tool will take as input a binary program. It will use disassemblers IDAPRO and JAXTAP to extract the assembly program from this binary one. Then we will compute our pushdown system from the assembly program. Our tool will also take some malicious behavior specified in our logics. And then we will apply our model checking algorithm to check whether the pushdown system corresponding to the program satisfies one of these malicious behaviors or not. If yes, then the program is declared as a malware. If not, then it is declared as benign. So our tool was able to detect more than 800 malwares. We checked also 400 real benign programs from Windows XP systems. So benign programs were proved to be benign with only 3 false positives. Our tool was also able to detect 200 new malware generated by 2 malware creators, and to analyze the flame malware that was not detected for more than 5 years by any antivirus. So we wanted to compare our tool with real antiviruses. So for that, we cannot use known malware. Why is that? Because for known malware, The known malware have known signatures. And so all the existing antiviruses, they have the signatures of these known malwares in their databases. And so to have a fair comparison with the known antiviruses, we needed to compare our tool with these antiviruses using new malware. This is why we used these two malware generators, NGVCK and VCL32, and we created 200 new malwares. So 100 using the tool NGVCK and 100 using the tool VCL32. As you can see, our tool was able to detect all of these new malwares, whereas none of the existing commercial antiviruses was able to detect all these new malwares. Our tool was also able to detect the malware Flame, which was used for cyber espionage in Middle Eastern countries like Iran for more than 5 years. And it was not detected by any antivirus, and our tool was able to detect it. Okay, now, as I told you, to summarize a little bit, so to perform malware detection, we use pushdown system to represent binary code, and we use some logics to represent malicious behavior. But pushdown systems are not precise enough. Why is that? Because they cannot take into account self-modifying code. So what is self-modifying code? Self-modifying code is code that modifies its own instructions during execution. And it is widely used in malware because it's used for obfuscation, to evade from antiviruses, to evade from static analyzers, etc. So let's take this example. So this is the binary code, and this is the address here. So, and this is the corresponding assembly instructions of this binary code. So FF is the binary code of a push. Therefore, this binary code is represented by this instruction. 8F is the binary code of pop. So this is represented by this, etc. So let's see how this works. So let's execute this. So first it will perform a push, then it will perform a pop, then we reach here move B. So what does this mean this? Move B0C02 means that it will replace the first byte in address 02, which is 8F, by 0C. So this means 8F04 is replaced by 0C04. And 0C is the binary code of a jump. So this means that this instruction is replaced by this one. Okay? So this is a self-modifying code. So if you compute the control flow graph of this piece of code without seeing the self-modifying code here, then we will use this control flow graph. Push followed by a pop, followed by move B, followed by jump to 2, and in address 2, I have the pop. So this is the wrong control flow graph. Now, if I consider the semantics of this move B, then this would be the correct control flow graph. I have a push followed by a pop, followed by a move, followed by jump, and jump, when I jump to address 2, now in address 2, I have this jump. And the jump 4, I will jump here. So this is the correct control flow graph. So you see that it is very important to consider these self-modifying instructions. And our solution to this problem is to use self-modifying push-down systems. So what are these self-modifying push-down systems? They are mainly push-down systems that can modify their own instructions during execution. So we will simply add this kind of instructions, which say, if I am in control point P, and I have R1 in my set of instructions, then remove this R1 and replace it by R2, and then move to P prime. So for example, this is how I will model this piece of code using a self-modifying push-down system. So this is, if this rule corresponds to this instruction, and R2 corresponds to this instruction, then this instruction will be represented by this rule, which says remove R1 and replace it by R2. So we presented a model checking algorithm for this self-modifying push-down system. And then we implemented our techniques in a tool for malware detection, which is based on self-modifying push-down system. Okay? And so it checks whether the self-modifying push-down system satisfies some malicious behavior or not. If yes, then it is declared as a malware. If not, it is declared as benign. So we did experiments with our new tool. It was able to detect more than 895 self-modifying malware. It was also able to check that 200 real benign programs from Windows XP systems were benign. And same as previously, we wanted to compare it with the existing commercial antiviruses. This is why we created 200 new malwares. And okay, so this is the result. We created 200 new malwares, and our tool was able to detect all of them, whereas none of the existing antiviruses was able to detect all the new malwares. Okay, now to end with, should I end now or how much time do I have left?
5 minutes.
Okay. Ouais. Okay, so as I said, now our tool, it will take some binary program as input, but also it will take some malicious behaviors specified in some logic as input. And the question is, how to generate all these malicious behaviors? How to generate them? Well, in the work that I presented, my students, they would read the assembly code of malwares, carefully read them. They will spend days and days reading them, and then they will try to understand them and to try to extract from them manually the piece of code or the that is responsible for the malicious behavior. As you can imagine, this is like a huge amount of engineering effort that necessitates a huge a huge amount of time and a huge effort. And so the challenge is how to make this step automatically. And this is what we did. Our goal was to extract automatically these malicious behaviors. So how to do this? To be able to do this, we need to find an adequate model for malicious behavior that can be extracted, that can be computed automatically. So what is a good model for malicious behavior? So let's see at the example of a Trojan downloader. So a Trojan downloader will transfer data from internet into a file stored in the system folder, and then it will execute this file. So this is an example of a Trojan downloader. So it will first call this get system directory A to get the path of the system folder. Then it will call this API function to transfer data from an URL address into a file. And then it will call winexec to execute this file in the system folder. And so to represent this behavior, we can use this malicious API graph. This malicious API graph, which says first execute this API, then this one, then this one. And if we have this sequence, then it's malware. And so the question is how to extract such graph automatically. And so we applied some techniques of, we applied some techniques of the IR community. Okay? So our goal is, given a set of malwares and a set of binaries, we will compute API call graphs that represent all these malwares, and then we wanted to extract the malicious graphs from all these graphs. Okay? So our goal was to isolate the few relevant subgraphs from the non-relevant ones. And for that, we applied some learning techniques from the IR community, and we obtained very interesting results. We obtained very interesting, malicious API graphs that represent malwares. Okay, I think that's it. Thank you.
Merci. Merci. Taïsir Touili, we listen to your questions. The first.
Thank you. Where can we buy your antivirus software?
We don't sell it. I mean, it's for research now, but we are working on making it available to the industry, etc. We are working on that.
Thank you. How do you know if there are a lot of false positives when you are computing this tool?
How do we know whether it's false positive or not? We know, because we know whether the program is a malware or not. So we know. So if the tool tells us it's a malware, it's okay. You understand? We no. Yeah.
Another questions? Alors, une dernière.
I see that you used Windows XP to make your tests. What about the new generation of Windows 11? The result can be the same, or that be a change?
We think it can be the same, but we didn't check. But there is no reason why it's not the same.
I have a little question about the fact that you said that you extract malicious software and store it somewhere. My main question is, the malware being extracted, is it stored like locally of an app, or is it stored on the cloud?
No, for now, what we have is that you give manually a program to the tool and you ask him whether this program is malicious or not. For now, yeah.